And I'm Jana with Northwest Cider Association. Thank you so much for tuning in and joining us on the third day of our first annual Northwest Cider Symposium. It's been really fun to be able to be live with our community in this virtual format, and we really appreciate folks taking the time and joining us and tuning in. And really excited that we get to speak with Jasha today from Enartis and talk about canned cider shelf life improvement. This is a very vital topic to many cider makers. So without further ado, I will turn it right over. I will just make a couple notes housekeeping wise. We've got that chat lit up, so please feel free to go ahead and put questions, comments in there. We'll track those as we go. Also, we'll have some time for Q&A at the end, so definitely feel free to make sure you save up important questions you want addressed, and we'll get those tackled. The entire presentation will be recorded, so you'll have access to it later. And if you need anything tech-wise or otherwise as we get going, please just feel free to direct message me. And I'm going to hop off the screen and turn it over to you. Thank you so much, Jasha, for being here.
Yeah, thank you, Jana, for the introduction and for having me here. And I just want to thank the organizers of the Northwest Cider Association for allowing Enartis and myself the opportunity to present on this topic today. So what we're going to talk about today is canned cider shelf life improvement. So again, my name is Jasha Karasek. I'm a winemaking specialist with Enartis USA. So I primarily work in the wine world, but over the last several years, I've had the opportunity and privilege to get to work in cider as well. So my work generally, is around wine. So I may use the term wine a couple of times in this presentation, and please forgive me for that. I'm just used to talking about wine a lot more than cider. But this topic, I feel, actually bridges wine and cider pretty strongly because canned shelf life, both wine and cider are kind of pushing into the can segment stronger with each year. And both kind of have the same kind of shelf life issues that we see in both segments. So I'm going to present a decent amount of data that's been collected over the last several years looking at shelf life improvement in wine. So we have more data in wine at this point, but we do have a significant amount in cider as well. And really the data crosses over between the two. So as you'll see, we sort of started investigating some of the shelf life issues in wine originally. And then when we discovered that they are prevalent in both wine and cider, we started to apply those same sort of principles in cider in terms of treatments and in terms of remediation of shelf life issues. And we found that there was crossover and that the two were essentially the same. So with that preamble, I'm just going to go over my agenda for the presentation today. I'm going to take about 30 minutes on my presentation, so I won't take up the full segment. We'll have plenty of time for questions at the end. We're going to talk about canned packaging shelf life issues, the most common ones that we see in canned cider. We'll talk about the impact of SO2, which is one of the big one of the main sort of factors we need to consider for shelf life issues in canned cider. And then we'll talk about Copperbound Sulfides as well, which also play a strong role in shelf life. We'll talk about solutions for these issues. So some of the solutions that Enartis has sort of pioneered for canned ciders. And then we'll talk about some other potential newer ideas that we can sort of look at for continuing to improve the shelf life of ciders going forward. So when we're talking about canned packaging issues, there are sort of main shelf life issues that we want to consider when we're talking about cider. Mainly, we're talking about reduction. So in canned ciders, we have received several reports over the years about the presence of some reduction appearing in canned ciders. And when I talk about reduction, I'm talking about volatile sulfur compounds like hydrogen sulfide, mercaptans, and these sort of compounds that are essentially not really well appreciated in ciders. So hydrogen sulfide is a sort of eggy aroma that can appear at lower levels. It tends to diminish freshness. At higher levels, it's just it's pretty bad. It's just very eggy and not appealing. But also other sulfur-containing compounds like mercaptans and disulfides can also evolve in the can as well, and those compounds are also equally unpleasant. So while we have seen some shelf life issues in terms of oxidation that can occur in canned ciders, and I'll talk more about that kind of in detail later in the presentation. The main issues we're seeing are reduction, and that's primarily because of the can itself. So the main characteristics of cans that can sort of preamble reduction is that it's a no oxygen transfer package segment. So a can is a sealed environment, doesn't allow any oxygen transfer. And that's sort of the definition of a reductive environment, where we don't have any oxygen ingress. We have a lot more of a reductive environment. And with that, we can have the evolution of sulfides. In particular, we think that the segment of copper-bound sulfides is really important in this particular environment. So we can have copper sulfides re-release, and I'll talk more about copper sulfides in a few minutes. The other sort of situation that we're seeing is potential issues with the liner. So liner permeation or contact between the product inside the liner and the aluminum can, which you do not want to happen. So the can is essentially a bag inside of an aluminum exterior. The liner acts like a sort of layer between the aluminum and the cider itself. And if you have any kind of deterioration of that liner and you have contact between the aluminum and the cider, that is not a good thing. And in general, we think that there is some evidence that there is some issues with the liners in terms of permeation of cider constituents and reaction between the aluminum and the cider itself. So that's another sort of issue, and that kind of leads into SO2 and the role that SO2 plays in this can environment. So now I'm going to sort of talk about the impact of SO2. So really, I'm going to talk about two sort of factors that are important for reduction evolving in can cider: SO2 and copper-bound sulfides. SO2 is the first sort of thing that I'll sort of touch on. So SO2 is an important preservative in cider, right? It's an antimicrobial agent, it's an antioxidant agent, it preserves freshness. And classically, SO2 in bottles did not sort of present any real kind of major issues in terms of reduction evolving. But as cideries started to use cans more often, and the liners inside the cans have been evolving over time, we've started to see a larger sort of issue in terms of reduction evolving. And we think SO2 has a really strong role to play in this. So we have seen that SO2 has been shown to impact reduction in canned products. You'll notice the equation kind of down here on the right-hand side. This is sort of the chemical reaction that we think is happening, which is that the SO2, which is in sort of aqueous solution, is potentially reacting with aluminum in the presence of protons that sort of deteriorates the aluminum and dissolves the aluminum, forming H2S and water. So that's a sort of basic reaction that we have concern with. So we think the liners have a large role to play in this situation because they are the barrier between the aluminum and the product itself. We think that pH has a large role to play in this conversion because what we've seen is that lower pH products tend to have this issue a little bit more prevalently than higher pH. When we talk about higher pH, we're talking about pH above 3.5, and below 3.5 would be lower pH. And then we think SO2 concentration has a significant impact on this as well. So the amount of SO2 that's present in the product is very important. So does the product actually come in contact with the aluminum? This is some data that was collected looking at different beverages in can. And you can see here that cider over the course of 9 months, when we look at aluminum concentration increases over time, we do see that over 9 months, there is an increase in the concentration of aluminum in those products. So what that tells us is that the aluminum is potentially making contact with the product and dissolving into solution. So this is work that was conducted at the AWRI. In general, our partners down in Australia have done amazing work in looking at the can segment. And so we're very grateful to have collaboration with them on this. The AWRI and Charles Sturt University in general have been great partners in this kind of work that we've been working on. And they collected a lot of the data we have so far looking at the impact of SO2 and different treatments on canned beverages. When we look, so this is an example of the interior of a wine that was in can. So this is not cider, but wine, but I think it's a interesting example of the interior of the can itself. And what was seen is that over the period of aging, there was actual pitting present on the surface of the aluminum inside of the can. So we think that this is the evidence of corrosion occurring on the interior of the can surface as well. So some actual visual evidence of this occurring. And these are microscopic sort of pores forming on the surface, or little blisters even forming on the surface. So the impact of aluminum on hydrogen sulfide has been defined as well from that same research university. Eric Wilkes presented this in our last webinar that we did last year on canning. And essentially what we looked at was the influence of aluminum foil or aluminum on the evolution of hydrogen sulfide. And so we can see the concentration of hydrogen sulfide is on the y-axis here, and I'm sorry, the concentration of sulfides is on the y-axis. We have hydrogen sulfide and methane thiol, which is sort of a garlicky kind of reductive note. And you can see that over the course of 8 weeks, when we compare the control and the control which has had aluminum foil added, we have a significant increase in the hydrogen sulfide in that product. So if we have contact between the aluminum and the cider or the wine or whatever beverage that has the SO2 in it, we're seeing a big jump in the hydrogen sulfide. So this leads to aluminum as being something that we can track in the canning process to kind of see how our liners are holding up or how the product is holding up in the can, because we can see a measurable increase in aluminum over time, and because we know that it impacts the evolution of hydrogen sulfide as well. I mentioned that the concentration of SO2 we think is important for the evolution of these reductive compounds as well. So I just showed you the impact of the foil in terms of the aluminum on the evolution of hydrogen sulfide. But also if we were to lower the SO2 of the medium, and so on the very right side, you'll see the peroxide and aluminum foil treatment. That's over the course of 8 weeks of aging. The peroxide treatment basically lowered the SO2 compared to the control or compared to the aluminum foil treatment. So in the presence of SO2, the aluminum foil produces a lot of H2S. If we decrease the SO2 with, let's say, peroxide in this case, or if we have lower SO2 levels in general, we produce less H2S even when we're in contact with that aluminum foil. So that's just a little bit of evidence in terms of the importance of the concentration of SO2 on this reaction. So that's basically, in a nutshell, the impact of SO2 on cider in terms of its effects on reduction appearing. So we've seen that SO2 has an impact on the increase of H2S, and we've seen that it occurs basically when there's some concentration of aluminum foil present. So moving on to sort of the second kind of part of the reduction that can appear in can is related to copper-bound sulfides. So copper-bound sulfides can basically be prevalent in both wine and cider. If you have a reductive cider, many times cider makers will treat the cider with copper sulfate in order to alleviate that reduction. So this is something that's been done for a long time. It was previously thought that when you treat a cider with copper sulfate to alleviate any reduction in the cider making process, that copper sulfate would form an insoluble precipitate that can either settle out of the cider or that you can essentially filter off of and remove from the cider itself. And so this was sort of the prevailing theory for a long time. And this was sort of proven in a model solution originally when they were looking at this sort of situation. So they looked at a model situation or a model wine when they first looked at this sort of interaction. And they sort of they took that model situation, they applied it to regular wine. But what has been discovered in the last couple of years is that that is not exactly the case. And actually, the copper that's bound to these sulfides remains in suspension many times in the cider and can make its way through filters even into the cider post-packaging. And so what you have is these microscopic copper sulfide compounds that are present in the cider. And what we believe is happening is that in the reductive environment of the can, once the oxygen basically is depleted from the packaging, this evolution of hydrogen sulfide is coming from this latent source of copper sulfide that's present in the can. So with this information, the idea is like, is there something that we can do to prevent this from occurring? Is there something that we can do to remove that copper sulfate? So now I'm just going to show you a little bit of the data that was collected. And this was done in wine, but again, it's going to be a very similar situation in cider. Essentially what they looked at was if they had a amount of copper present in a wine, treat it with, or if they had hydrogen sulfide and they treat it with copper, would that copper be removed with filtration? And they showed that in a model solution, that was the case, that you could actually remove the copper sulfate. But as they increased the actual concentration of wine in that model solution, that no longer held true. So essentially what they proved here is that, in a model situation, copper binds to sulfur and it precipitates. But in an actual wine, it actually does not do the same thing. So it's interesting information. I think it's pretty groundbreaking for the industry as well in terms of looking at these copper sulfides that can remain in the product post-packaging, even through filtration. So this is a 0.45 and a 0.2 micron filtration. And essentially, after filtration, almost 100% of the solution remains. So the AWRI also looked at the impact of removing these copper sulfides on the reduction that can appear. And so they looked at the control and they looked at when that copper sulfide was stripped out with PVI PVP, which is a polymer I'll talk about in a couple of minutes. But basically it's a polymer that can remove metals, and they've actually discovered that it can remove metals that are bound to sulfides as well. So when we just remove the metals without the presence of aluminum, we do see that it eliminates the reduction that can appear. I will also point out that these levels of reduction that you're seeing on this chart are 5 micrograms per liter at its lowest point in the control. 5 micrograms per liter of hydrogen sulfide is going to be it's going to be reductive because the sensory threshold of hydrogen sulfide is 2 micrograms per liter. And so it's going to be prevalent even at 5 micrograms per liter. At 50 micrograms per liter, that is going to be a horrible situation in terms of reduction. It's going to be very, very eggy and unpleasant. Not something you would want your customers to be exposed to. So what they found is that with some of these levels of reduction that can appear after 2 and 4 weeks can be alleviated by stripping out some of those copper sulfides. We found that when we stripped out those copper sulfides, that even in the presence of the aluminum foil, while we did have reduction appear and a large spike, if you remember the previous slide I showed you, this same product had about 45 or 50 micrograms per liter of hydrogen sulfide. So it seems to be helping, at least in this situation with the hydrogen sulfide evolution when we're in the presence of aluminum foil. So what that means is that if we didn't have a liner degradation in our cider, we would still benefit from treating to remove copperbound sulfides. But if we have deterioration of the liner and we have SO2 present that can react with the aluminum, that's still going to be a problem. So what we really have to consider is that if we have a pool of copperbound sulfides, we need to address that, or you're still going to have reduction. Until the liner situation gets better for canned ciders, what we're going to need to do is lower SO2 levels to ensure that we don't have this reaction between the SO2 and the aluminum as well. So we need to really address both of those aspects to really ensure that we don't have reduction appear in this packaging. So now I'm going to sort of switch gears and talk about some of the agents that are available for removing copperbound sulfides. So I mentioned PVI PVP already. This is a polymer that's been around for a while now in the industry, but is just now starting to gain traction in terms of its use for removing metals. And in particular, for can packaging, we now know that it removes these copperbound sulfides, which can alleviate some of the reduction that can appear post-packaging. It also is a finding agent that can remove some bitter hydroxycinnamates and smaller phenolic compounds as well. And then there's chitosan. So chitosan is a pretty cool tool for cider makers. In one form, in one kind of processed form, it acts like an antimicrobial agent. So chitosan in one form can be an antimicrobial agent. If it's processed in such a way, it can actually become a fining agent. And that fining agent can actually bind to metals and remove them as well. And so we found that chitosan is also a useful tool for removing these copper-bound sulfides. And with this information, we basically created a blend of our pre-activated chitosan for removing metals and the PVI PVP, and that's called Claral HM. And so that has been our sort of our best tool in terms of removing these copper-bound sulfides. And I'll show more about the comparison between just the PVI PVP and the blend of the two in terms of its ability to remove copper-bound sulfides. So this is, again, data that was collected from our friends down in Australia. And I'll just quickly go over what this chart is. This is, again, a wine. So not exactly a cider, but it's going to be a similar impact in cider as well. And essentially, the left portion of this graph, the TO, control, ST, and CL, is with no copper added. The right three bars are going to be with copper added. So this wine had a base of 0.3 milligrams per liter of non-labile copper. So I'll just briefly go over what labile copper versus non-labile copper is. So labile copper is copper that's not bound to anything. It's just sort of freely in solution. Non-labile copper, in terms of this graph, is copper that is bound to something, either sulfides or thiols or sulfidrals. And so the non-labile copper fraction is really what we're concerned with in terms of canning, because the non-labile fraction acts like a reservoir of reduction that can re-release in the can. The labile fraction is not as important that we think at this point in terms of reduction appearing post packaging. So the ST on this graph, if you look at the left four bars, there's the control, the ST, and the CL. The ST is stable met alone, so treating with PVI PVP alone. So PVI PVP, we have a commercial product called stable met, which is just the PVI PVP. And so if we were to just treat with that, it does drop down the level of copper-bound sulfides by half. But then the CL is actually the Claral HM, the blend of the PVI PVP and the chitosan, and it significantly reduced the level of copper-bound sulfides almost down to zero. So we think the Claral HM is actually a great treatment for this. The right three bars basically show the impact of both of those treatments on labile copper, and it actually shows that those compounds, the stable met and the Claral HM, are better at removing the copper-bound sulfides than the labile fraction, which is, I think, interesting in terms of its impact on canning. So that's kind of the idea behind using these polymers, is that they can essentially remove the copper-bound sulfides that act like a latent source of reduction. Another thing that I've heard from cider makers is that they never add copper sulfate to their ciders, and they never have to deal with adding copper sulfate. But another sort of idea that I want to potentially touch on is that there's natural levels of copper that come in with apple juice. So these aren't like toxic levels of copper, they're just natural levels of copper that are present in the juice. You know, apples have copper as a micronutrient present naturally in them. And so this is an example of 9 different batches of juice that were brought into a cidery. And you can see there's some variance in terms of the levels of copper, but just sort of coming in naturally, we have almost 0.2 milligrams per liter, which is, I think, a fairly significant amount of copper just to have coming in naturally. Now, it's obviously still fairly low in terms of when we make an addition of copper sulfate, we're looking to add like 0.3 to 1 ppm of copper, and this is around 0.2 at its highest level. So there is going to be some natural copper present in the juice, and my question is to cider makers, and I hope that we can find an answer to this, is does that copper potentially bind to any sulfides that might be produced in the fermentation and remain in the cider going forward? Because we know that it doesn't precipitate if it reacts with sulfur compounds. And so that's a question that I'm hoping to answer over time, is to find out if that natural copper can bind to sulfides produced in the fermentation and remain in the cider post-packaging. So that's something that I hope to answer in the future. And it's just, the reason why I included this is just to open up the discussion of natural copper levels present in juice. Another question I have is the prevalence of copper sprays in organic orchards and whether that can play a role in the copper levels of the juice that are coming in as well. So all some interesting things that I hope to look at in the future. So now I want to show some actual canning trials that we did. I believe we presented some of this data last year and previously in other presentations, but if you haven't seen it yet, this is, I think, a pretty good example of how some of the theory and experimental work that was done was applied in a practical manner to achieve a good result. So we had a trial that was done at a cidery in California, looking at a control which had a normal level of 30 ppm of SO2, and then our sort of trial, which was looking at removing copper-bound sulfides with Clairol HM and 0 SO2 over the course of the cider making process. So the trial is sort of supposed to be our method for eliminating reduction from both of those fronts, removing the copper sulfides and eliminating the factor of SO2. So what we did is we tracked this cider trial over time, and we looked at the normal SO2 addition compared to our no SO2 protocol. And we found that there was a significant reduction in the amount of aluminum that evolved over time in this canned product. So this is pointing to the potential reduction of corrosion of aluminum and an actual reaction between SO2 and aluminum in those products. So pretty evident that there was a large reduction in the amount of aluminum that dissolved over time in those products. And then we also tracked the hydrogen sulfide over time between the two different treatments. In the normal SO2 addition, we found that the hydrogen sulfide went up upwards of 3.5 micrograms per liter, which is above sensory threshold at 2 micrograms per liter. So there was reduction present on that cider, where the no SO2 protocol had no hydrogen sulfide evolved and had no reduction, no detectable levels of hydrogen sulfide. So I think this was pretty good results in terms of eliminating the reduction from this potential cider. So some takeaways from that trial: we found that the copper sulfide removal was successful with the Clairol HM. The no SO2 helped to eliminate the hydrogen sulfide. We did find that this cider, however, had some slight oxidation apparent post-packaging. And we were kind of leery about that potential issue with doing no SO2. And so we did get a little bit of oxidation. It wasn't a lot, but just a tiny bit. And so with that, we know now that the oxygen pickup at packaging is critical because if you can maintain the cider over the course of the cider making process and maintain lower levels of SO2, when you get to packaging, if you can very strongly control the level of oxygen, you can limit essentially the oxidation that can happen in the packaging. Because remember, there's no oxygen coming into the package post-packaging. It's really the oxygen pickup, at packaging that's going to affect any potential oxidation. And so we still need a solution for this potential oxidation. So no SO2 might not be possible at this time, but a small amount of SO2 I think is definitely more reasonable in terms of having a small amount of SO2 to accommodate for any oxidation that may be picked up at canning. So this really depends. How much SO2 you need to use really depends on how tight your control of oxygen is at packaging. If you have really tight control, you could probably go with lower SO2. Between 5 and 10 milligrams per liter might be possible. But if you have a decent amount of oxygen or you don't have a lot of control over oxygen pickup, then you might need to go with a higher amount of SO2 to accommodate for that situation. So in general, you will still benefit from lowering your SO2 at packaging. But if you're going to go with no SO2, you need to have something else to buffer that oxidation that can happen. And so that's where some of the ideas for next steps for progressing in this category come. So if we're looking at replacing SO2 or trying to lower SO2 levels, what we're really looking at is 3 different things that SO2 does in cider. It acts as an antioxidant. it acts as an antimicrobial, and it acts as an antioxidasic. So the antioxidasic activity, I think, is probably less important in terms of shelf life. What I'm more concerned about is antioxidant, antimicrobial activity. If we are able to maintain a spoilage-free environment over the course of the cider making process, post-packaging, we can control microbes with a lot of different tools, either Velcorin or sterile filtration or pasteurization. There's a lot of different options for that. So really my main concern with So2 replacement is the antioxidant function of So2. I think basically a new tool that just became available at Enartis is this antioxidant microbiostatic tannin blend called Hideki. And so this just became available in February, so it's a newer tannin for our portfolio. And it's basically a blend of a special kind of gallic, ellagic, and condensed tannin. It's fairly neutral in terms of its mouthfeel effect. I find that it basically fills the mid palate a little bit and gives a little bit of kind of zest to the mid palate of the cider. And then the aroma impact, it doesn't really have an aromatic contribution, but its technical implications for microbiostatic and antioxidant purposes are actually quite good. So what we found is that most of the trials we've done so far are in wine, by the way. So we're planning trials right now in cider, and we're looking forward to seeing its use in cider, but I'll just show you some data from wine at this point. So what we've seen is that in terms of its impact on browning or increases in oxidation reactions, when we compared a oxygen-saturated wine, which is the control, to that same wine treated with So2 with 5 grams per hectoliter of Hideki, and then 10 ppm of So2 and 5 grams per hectoliter of Hideki. We saw a dramatic decrease, obviously, with the So2 in terms of the browning increase, but we also saw a significant decrease in browning with just the Hideki alone, and even better results with a small amount of So2 and 5 grams per hectoliter of Hideki. So I think the Hideki could be an interesting option in combination with low So2 for lowering So2 levels in terms of its antioxidant impact. And I think that in combination with a small finding of Claral HM, if you have copper-bound sulfides, could be sort of a good solution for avoiding reduction entirely. And then also avoiding any potential oxidation that could come with canning at such low So2 levels. So we also looked at the impact of acetaldehyde with that same sort of treatment in mind, where we saturated a white wine in air for 6 days. We compared the acetaldehyde increase in the control versus 1 gram per hectoliter, 5 gram per hectoliter, and then combinations of Hideki and So2. And we saw fairly good results in terms of all those treatments for reduction of acetaldehyde. So we think that this could be an interesting sort of buffer for oxidation in this instance as well. So there's definitely more work to be done in the canning space in terms of shelf life, and it's something we want to continue to progress on. We've learned a lot in the last 3 years, and I think the information is going to be really helpful for the cider industry going forward, and in particular in this package segment. But there's definitely more work to be done. We want to determine the usefulness of tannin as an antioxidant in canned products. So it's still experimental at this point in terms of its use in canned products, but we think it could be very useful. We want to find out how prevalent copper-bound sulfides are in ciders that have had no copper added. And this is possible now because of newer analysis that's becoming available to the industry. So a researcher in Australia has developed a spectrophotometric method to do this. And so spectrophotometers are very common in a lot of labs. And so it's a fairly straightforward analysis that can be done. But instead of measuring just total copper, which is what has been classically done, this method can actually measure the bound copper. And so with that, we can start to understand benchmarks for ciders in terms of copper-bound sulfides, and also understand how important those copper-bound sulfides are for reduction, and whether or not a cider would need to be treated with Claral HM before it goes into the can. So that's work that we need to start doing in terms of benchmarking these levels and understanding how important they are. So that leads into the next point. So how do we know if we have copper-bound sulfides and require treatment with Claral HM? that's something that we want to continue to progress on. And that spectrophotometric method I mentioned, I think is going to be really useful for that. So in conclusion, we know the culprits of reduction in cans at this point are related to SO2 and copper-bound sulfides. We need to lower SO2 levels to avoid reduction problems at this time. Until liners can become more robust, this is something that we need to consider and do. Treating with Claryl HM or stable MET or just regular PBI, PVP will remove those copper-bound sulfides that are responsible for H2S after packaging. And then managing DO and utilizing tannin can potentially help lower SO2 levels at packaging as well. So that's something that we can start to tighten up on is managing those DO levels, and possibly look at using tannin to lower those SO2 levels at packaging also. And with that, that will conclude my presentation portion of this, or the actual presentation itself. If we want to open up for questions now, I think we can just type questions into the chat box and I can answer them as we go. So if you guys have any questions, feel free to start typing them in the chat box. I'm also going to be available at our booth after this so that we can essentially, talk more about these sort of reduction issues and more about can packaging if you like. But I'll just give a few minutes in case anybody has any questions that they want to type in the chat box. I see a couple of questions in there already. One from Evid Singer. He asks, what is a good threshold for oxygen pickup in a low or no SO2 cider to prevent oxidation? I would say as little as possible, but certainly below, I would say 0.5 ppm is definitely a good target, but as low as you can possibly get it, essentially, because the oxygen does extend the amount of time before the reduction shows up. So you can think of it like a wick on a sort of reduction bomb in the can. Once the oxygen gets to 0, that's usually when we start to see those reductive compounds show up. But if you're treating with like Claryl HM, for example, as low as oxygen as you possibly can have is a better thing, because then you're essentially avoiding the oxidation that can come with that process. So Andy asks, are there commercial labs currently running the copper-bound sulfide analysis? We are starting to look at offering it as a service to collect data. So we have the method and the instrumentation to be able to do it, and we are actively looking at potential clients to work with on this benchmarking. But commercial labs are not keen on, or not aware, I think, of offering it yet, and so the demand for it. And so that's going to be something where it's sort of like, you have to have a certain amount of demand for commercial service before a lab will start offering it. And if a lab starts to receive requests for it, they'll start to look at it. And so it's sort of a chicken and egg kind of situation where you need to have the demand for it first in order to start offering it. But you need to have awareness of the analysis as well. So I'm hoping to start making cider makers aware of it so that we can start, getting commercial labs on board with offering it too. So Evan says, I'm used to the beer thresholds of 100 ppb or less. Just wanted to get some context for cider. Yeah, I mean, if you can get levels that low, I think that's great. The lower, the better. Any other questions? Raquel says, you mentioned Velcorin. If Velcorin is being dosed as canning, could you eliminate the use of free SO2 or using Hideki? So Velcorin is going to work as an antimicrobial agent. The free SO2 is not only antimicrobial, but also, and free SO2 isn't actually antimicrobial, it's actually more microbiostatic. So it actually prevents microbes from being able to grow. But if you have a population of bacteria or yeast and you have free SO2 and no other protection, that bacteria or yeast is going to take off eventually. But the Velcorin can replace, let's say, the antimicrobial impact of SO2, but it can't accommodate for any oxidation that might be picked up at canning. So I'm talking more about like the packaging itself in terms of when you're at packaging, when you get to that point, how do you prepare that cider for packaging? But really there's the whole process up until that point too that needs to be considered if you're lowering your SO2 levels. And so there's other tools that are available for for accommodating that situation. There's chitosan that can help as an antimicrobial. This hideki actually has microbiostatic capacity, so it could be used as sort of a buffer for processing as well. But those are all things that are somewhat new, so they're things that we need to start working on now. So to answer your question, I don't think that Velcro really can replace all of the impacts of free SO2, but it can help with the microbial aspect of it. Evan says, any research in comparing legacy epoxy versus non-BPA epoxy liners? We know that epoxy versus BPANI Gen 2 are better. So epoxy is the best option, but there's simply, I think, that those liners are not being sort of used as readily anymore because of regulations and things like that. But there's actually a lot of questions about the liners that are sort of being asked, and not really, the manufacturers of liners are not being as transparent as they could be with the industry in terms of what they're using and some of the testing they're doing and things like that. So I think the industry is kind of asking for that information, and we don't quite have it yet. But I will say that Cornell has been doing a lot of really good work on this sort of topic, in terms of they are actually actively looking at different polymers. Sorry, my computer's dying. They are actually looking at different polymers and different liners for specifics for wine and for cider. So I would check out some of the work that Cornell has done. Rachel Allison has been doing a lot of work on liners, and she would be the best resource for that kind of information. So thank you, everybody, for being here for this presentation. I appreciate your attention, and if you have questions, feel free to reach out to us or show up to our booth. And thanks for the opportunity. Thank you to the Northwest Cider Association for having me here today.